In this session, we're going to discuss representing graphs and graph isomorphism. So, specifically, we're going to define what is adjacency list, adjacency matrices, incidence matrices, and isomorphism of graphs. So, we have different ways in representing our graph. So, we could create a table like the adjacency list. Okay, so it is composed of two columns. So if it's a simple graph, the first column is vertex, the list of vertices, and second, the adjacent vertices or connected vertices on it. So for example, for A, so B and C and E are all connected to A, so it will be listed on the adjacent vertices. Same as with B, it is connected to A, so it will be listed on the second column for B. Okay, so another example is this graph. So it is a directed graph. So for a directed graph, the first column will be the initial vertex, and then the second column will be the terminal vertices. Okay, so for example, for A, so A is the origin of the path. Okay, so this initial vertex, the start point. So A goes possible goes go could go to B, to C, to D, and E. So I'm going to list it on the second column. Okay, that refers to A. For B, so we have a loop. So initial is B, end is B, and it is also connected to D. Okay, so there is a directed path going to D, so D is included in the terminal vertices. Okay, and same as with the other vertex. So that is adjacency list. So another way of representing our graph is using adjacency matrix. So it defines the connection of our vertices using a matrix. So we're going to write 0 if there is no connection, 1 if there is a connection. So for example, we have this graph. Okay, so the first column is intended for connection to A, second column connection for B, to B rather, and then third column connection to C, and fourth column connection to D. First row is we're going to define the connection for vertex A, second row vertex B, third row vertex C, and last row vertex D. Okay, so since the first row is intended for to define the connection to other vertices for A, so since there is no connection A or there's no loop for A, so that's why it's 0. And A is connected to all vertices, so that's why the rest is equivalent to 1. Okay, for B, so B is connected to A, so this is 1, and there's no loop within B, so this is 0, and it is connected to C, so that's why this is 1, and there's no connection between B and D, therefore this should be 0. Okay, and for C, so it is connected to A and B, so that's why this is 1, 1, but there's no connection between C and D, so that's why the fourth column is 0, and there's no loop, so that's why the third column is 0. For D, it is only connected to A, so that's why we have 1 in the first column, and the rest is equivalent to 0. Okay, and another example. So we have A, B, D, C here. So but still this is A, B, C, D. So A for first, B second column, third C column, D column. Again, the connection. Okay, this is the terminal vertex, yung column, and row is the initial. Okay, initial vertex. So A is connected to B and C. That's why this is 1, 1. So there's no loop for A, so this is 0, and there's no connection between A and D, so that's why it's 0. Okay, for B, it is connected to A, so that's why this is 1, but not connected to B and C. There's no loop within B. There's no connection, directly connection between B and C. So that's why this is 0, 0, and it is connected to D. That's why this is 1. Same as with C. This is connected to A, 1, but there's no connection between B and C. So that's why this is 0, no loop, 0, and connection. There's no connection between C and D, so this is 1. And last, for D, there's no connection between A and D, so that's why this is 0. There's no loop, 0, but it is connected with the other vertices, the B and C, so that's why this is 1, 1. Okay, so that's adjacent matrices. Okay, so another way of representing our graph is using incidence matrix. So here we need to define all the edges. We need to label all edges. Okay, so the edges will be the column. Okay, and still the rows represent the vertex, the initial vertex. Okay, so for example, we have 5 vertices here, V1 to V5. So first row is for V1, second row is for V2, third row is for V3, fourth row is for B4, and last B5 for the fifth column, fifth row rather. And and let's check the vertices, the edges rather. So we label it. So this is E1 that connects B1 and B4, B1 and B5 so that will be E2. So edge between B2 and B4 is E3, B2 and B5. We have E4, B2 and V3 is E6, and V3 and V5 is E5. Okay, so column is represented by the edges. So that's why we need to label it. So we're going to have a value of 1 if we have E1. If we don't have E1, it will be 0. Same as with the other edges. So for example, for V1, we have E1 and E2. That's why this is 1, 1. And the rest will be 0. Okay. For vertex 2, the edges connected to V2 are E3, E4, and E6. So that's why this is 1, 1, and 1, and the rest are 0. For B5, it is connected to E2, E4, and E5. So this is E2, that's why this is 1, E4, and E5, and the rest are 0. Okay, so that's a simple graph and incidence matrix. For pseudograph and incident matrix, it's the same. Okay, loop will be considered as one edge. Okay, so we have 5 vertices, same, V1, V2, V3, V4, V5, label all edges. Okay, so to define the value of, or what edge represent our columns. This is E1 to E8. Same logic based on our previous example. So for example, V1, so what are the edges connected to V1? So they are E1, E2, and E3. So that's why all values here are 1 and the rest will be 0. And for V2, it is connected to E2, E4, E3, E7, and E6. So we have 5 edges connected to V2. So they're all equivalent to 1 and the rest will be 0. Okay, so that will be pseudograph and incident matrix. Okay, so again, we have adjacency matrix, incidence matrix, and adjacency list to define to define our, or to represent our graph in a different way. Okay, so now let's move on with the isomorphism of graph. So basically, isomorphism of graph um, give, it means that two graphs are equivalent based on the properties of because of they have the same properties. Okay, so for example, we have 4 vertices in graph 1, We also have 4 vertices in graph 2. The connection between the vertices is the same with the connection of the second graph. The only difference is how we draw it. Okay? But V1, there's corresponding vertex 1 in equivalent to vertex 1 in the second graph. Same as with vertex 2 in first graph. There is equivalent vertex 2 in the second graph. Okay? So that's isomorphism. Okay? So for example, we have this graph 1 and graph 2. So we're going to label each vertices in graph G as U. So U1, U2, U3, and U4. And for graph H, we have V1, V2, V3, and V4. As you can see here, it is drawn differently. Okay, so let's see if the connection or the edges, okay, or the vertices, the connection of the vertices are the same. Okay, so first, do they have the same edges? Yes, we have 4. Do they have the same number of vertices? Yes, we have 4. Now let's check, okay, which vertices are equivalent between these two graphs. So let's suppose U1 is the same as V1. Okay, so let's say U1 is the same as V1. So the property of U1 should be the same as V1. Okay, so U1 is connected to a vertex. Okay, so it has a 2 adjacent vertices, U2 and U3. Okay, so U1, V1. So V1 here, it also have 2 vertices connected to it, V3 and V4. Okay, all right. Now, V3. So it is connected to 2 adjacent matrix, U1 and U4. So V3 is connected to V1, which is equivalent to U1. So tama na tayo sa part na to, dito sa line na to, because behavior of this edge is the same as the behavior of U1 and U3. Okay, now V3 is connected to V2, which is not, diba? Dito, U4 ang connection ng U3. So, U3 is connected to U4. Okay? So, dito sa graph na to, ang V2 ang equivalent sa U4. Okay? V2 is equivalent to U4. V3 is connected to V2. U3 is connected to U4. So, ito yung equivalent ng edge na to, ito, sa graph na to. Okay? So, tama na tayo sa U3, tama na tayo sa U1. Now, sa U4 tayo, which is equivalent to V2. Si U4 connected sa U2. Okay, which is, yung U2 dito is equivalent to V4. Kasi yun yung nakakonect kay V1, si V4. So, tama ba nakakonect si U4, kay U2? Dito, yung equivalent yung vertex? Yes. V2 is connected to V4. Okay? V2 is U4, U2 is V4. So therefore, this edge is actually this edge. Okay? And the U3 and U4, again, this is the edge equivalent to it. Okay? As you can see here in this slide, even though they have different layout, but the connection, the edges, okay, or the property of the edges and the vertices, how they are connected, are the same. Okay, so therefore, these two graphs could be considered as isomorphic. Okay, they are equivalent based on how vertices are connected. Okay, so there's equivalent between vertices. Okay, so that's isomorphism of graph. So another example, graph G and graph H, are they equivalent? Definitely no. Why? If you're going to equivalent A to S, they are equal sa S and V, A and D. Ito yung equivalent between these two sides and these two graph, A and B, equivalent to S and T. But there's no connection between A and E that would represent S and W dito sa first graph natin. So they are not equal. Kasi dito, B and F, there's no connection between T and X. That's why they are not equivalent. Okay? So be sure there is equivalent. Okay? Now, so that's it for this video lecture. Okay? So if you have any question about how to represent our graphs in different way and graph isomorphism, so kindly send me a video lecture. So on the next video lecture, kindly send me a message, rather not the video lecture. Kindly send me a message if you have some questions. But in case, so on the next video lecture, we're going to answer some problems from our book. So thank you and see you on the next video lecture. Thank you.